Hello to all of you and welcome back to my SP2 channel. This video is all about the acids, bases, and neutralization reactions. I'm going to start by the introduction for the acid and bases, strong acid and strong bases as well. I have a little bit on the neutralization reactions and how we get salts. There's another type of neutralization reactions that are producing gases. We're going to be looking at that too. And we also have a practice for you at the end. Okay, so starting by the acids. Acids are substances that ionize in aqueous solution to form hydrogen ions, which is known as H+. Now, when you're thinking of your hydrogen atoms, they consist of a proton and an electron. So if I have an H+, essentially I lost my electrons, right? So whatever is left over is going to be just a proton, and that's why you can call your acids as your proton donors. Acid also have a sour taste if you're thinking about how they taste, okay? And I have a couple of examples for you here. So the first example is hydrochloric acid, which is an acid that is produced in our stomach. The second one is sulfuric acid. That's an acid used in various industrial process. We have nitric acid. It's a very common acid in our fertilizers and explosives. We have acetic acid, which is my favorite, right? That's the one that we have it as vinegar, right? So pretty much acetic acid in a very low concentration would be your vinegar. And the last one is citric acid, which is an acid that you can find it in your citrus fruits. Okay, now for the bases, these are the substances that accept protons, or you can say they are producing hydroxide ions when you dissolve them in water. And therefore you can call them proton acceptors, right? Bases are going to have a better taste, and here are some common examples. So we have sodium hydroxide, commonly used in cleaning products and soap making. We have ammonia, commonly used in household cleansing and cleaning products. We have calcium hydroxide, which is commonly used in agriculture to neutralize acidic soils. Magnesium hydroxide, often we use that for antacid, for treatments of heartburn, or baking soda, right? That's the one that we use in our cooking and cleaning. Okay, now this slide is all about the kind of definition of the strong and weak acid and bases. Okay, so everybody listen up. In chemistry, to what degree our acid and bases dissociates, we're going to call them differently. Okay, so if I have an acid that is completely dissolved in water and releasing all of its protons, we can call that a strong acid. Best example is hydrochloric acid. That's a very common one. But if I have an acid that only does dissociation partially, right? Some of that dissociate, not all of that, then you can call that a weak acid, something like acetic acid. Now I'm going to say the same thing for the bases. If I have a strong base, they are going to completely dissociate into their hydroxides, right? When you dissolve them in water, something like sodium hydroxide. But if you have a weak base, they're going to have partial dissociation, right? Something like ammonia. Okay, so be careful with the usage of these two terms, strong and weak. It does have a very clear meaning in our chemistry world. Now, here is the list of the common strong acid and bases. I'm going to start by the strong acids. And as you can see, you have their names as well as their chemical formula. Okay, so I have hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, that's HI, high, right? Chloric acid, which is HClO3, perchloric acid, we have HClO4, nitric acid is HNO3. We also have sulfuric acid, and this acid has more than one proton. We'll talk about that in our future lectures, but for now, just consider only the first proton is going to be a strong acid, right? You only have complete dissociation for the first proton, not the second one. For the bases, we have shorter list, right? So we have all of the group 1 metal hydroxides, such as lithium, sodium, potassium, and cesium. And then we have some of the group 2 metal hydroxide, and those are calcium, strontium, and barium. Okay, now this is going to be all about the neutralization reactions and how we can produce salts. So I'm going to start by pretty much definition of neutralization reactions, okay? So these are the reactions that we have done between an acid and a base, and they are typically producing water and salt, okay? So here's my general equation. My reactant side, I have acid and base. On the product side, we have salt and water formation. So here's an example. Hydrochloric acid is my acid reacting with sodium hydroxide, and they are producing sodium chloride, which is my salt, as well as water. Now, because hydrochloric acid, sodium hydroxide, and sodium chloride, they all are completely water-soluble electrolytes, I'm going to write them as their separated ions. And you can also look at both your reactant side and product side. You can cross out your spectators, and those are going to be sodium and chloride. So whatever is left over is going to be your net ionic equation, which means that practically you have a reaction between proton and hydroxide that is forming water. So this is the actual acid-base reactions, right, that we have. For all other species, they're just there to balance out the charge, but they're not really doing anything other than that. Okay, so keep that in mind. The formation of water is a key for our neutralization reactions. Okay, so now take a look at this slide here. This is again the neutralization reactions, but it's slightly different. Okay, so what I have here is beside your hydroxide, there are many other bases that they can react with protons, and typically they are forming molecular compounds. Two of these are pretty common, and those are sulfide and carbonate anions. Okay, both of these anions are reacting with the acid, and they actually forming gases that they typically have very low solubility in water. So they're going to escape from your container. Okay, we're going to be looking at both of them, starting by your sulfide ion. And if you have a reaction with this anion and let's say hydrochloric acid, okay, and this is my sodium sulfide. Looking at the product side, we have H2S, which is hydrogen sulfide, and sodium chloride. Okay, so I'm going to look at my net ionic equation, meaning that you can cross out your sodium, right, your chloride, these are your spectators. So if you look at the leftover, it would be the reaction between your protons and your sulfide, and it's producing this compound, which is hydrogen sulfide, and it's a gas, right? And if you want to have a little bit more here, the smell of the, rotten eggs, the really bad smell is because of the formation of this gas, okay, the H2S. Okay. Okay, so here's the second one, which is the reaction with either carbonate or bicarbonate anion, right? They're going to be pretty much the same. I'm going to look at bicarbonate here for you, okay? So here's my hydrochloric acid reacting with your bicarbonate, and it's actually sodium bicarbonate, and it's producing sodium chloride and carbonic acid, okay? Now, here is important to note that carbonic acid is not stable, okay? It is going to decompose us to water and CO2 spontaneously, which is going to escape from the solution as a gas. So practically, you're going to have your carbonic acid that is pretty much converting to water and CO2. And CO2 is a gas, right? That's your carbon dioxide. So it's going to escape from your container, right? Okay, so if you look at your molecular equation, you have your hydrochloric acid, and then I have sodium bicarbonate. I still have my sodium chloride, but I'm just going to replace my carbonic acid with these two molecules. Okay, and again, you can cross out all of your spectators, right? Sodium is gone, chloride is gone. This will be your net ionic equation, right? Where we have a proton reacting with your bicarbonate and it's producing water and CO2. Okay, excellent. So here's our practice for you. So the question here, it says, what is the net ionic equation for the reaction between a stomach acid, which is hydrochloric acid, and we have this antacid, which is aluminum hydroxide. Okay, so looking at the first reaction, Reaction A. Thinking about it for a moment. Is that going to be our net ionic equation? Probably not, right? Because you still have your chloride, for example, on both sides of this equation, right? Now looking at B reaction. So it seems that reaction A is now balanced, right? But you still have your chloride. So that is going to be another nope, it's not what we're looking for. Finally, when you're looking at the third one, right, as you can see, chloride are all cancel out, which is our spectator. So yes, that is going to be our net ionic equation. Excellent. Okay, thank you very much for watching this video. If you found this video helpful, please don't forget to give it a thumbs up. You can share that with your friends. If you're enjoying the content and you want to keep learning with me, don't forget to subscribe. It means a lot to me if you can support my channel, and I'm going to have a lot more coming up for you very soon. Stay tuned for that. Take care. Bye-bye for now.